Okay, let me share my screen. So we talk about the metal printing last time, but that's like inkjet related matte printing, which is a new process. But actually, in the metal printing area, the dominant one is the powder-based processes. And today, let's look at some details about it. Sorry. So for the powder bed fusion-based processes, there are three major steps. One is you want to spread a layer of metal powder, and then scan an energy beam over the region of powder you wish to melt. Either use laser or electron beams. Then you repeat the first two steps. That's pretty much what the powder bed fusion does. So you can see it is quite similar to the selective laser sintering, which is also a powder-based process, but using the those polymer or elastics, plastic powders. But here we are using the metal powders. So that suggests a higher energy consumed to actually melt the powder of metal. So as you can see here, this becomes a focus in the industry because many parts in the real industry are made of powder. Made of metal. So that's why people are looking at these powder-based additive manufacturing processes, especially for those defense or aerospace industries. They want to produce large volumes, complex geometry, and lightweight parts, in which the metal powder-based processes are the best fit. So as you can see here, so there are more and more powder sold in recent years. As you can see, here shows the powder sale growth rate. It's around 50%. 49%. The increasing, and there are some projection for the sales of metal powders made here. Basically, it is projected to 2020 there will be 1.2 billion cost for the powder, and by 2025 this number will be doubled up, which is 2.4 billion. So that suggests a increasing application or needs in those industrial applications. I think you have a tour. You had a tour in the Amperin Center as well as our labs, our Brinkmann lab. There are powder-based printer there, and they take large space, and also usually it costs quite a bit. It's very expensive, and that's what the status of this kind of processes. It can produce a really nice part with a high precision. And again, the complex geometry can be achieved using such a process. And let's look at some of the components for this powder bed fusion systems. Of course, there's a feeding system to feed the powder to the build tank. Also, there's a waste bin to collect those excess powders used in the processes, because especially when you spread the metal powder, there will be the excess powder to be pushed into this with the beam. And this can be recycled because that is super expensive. You don't want to waste it. Also, for the energy source of the powder-based process, there are the two primary ones are laser and electron beams. To enable each of the mechanism, each of the components work together, there are motion subsystems. For example, the energy beam steering. Also, the building platform will move up and down to enable the layer accumulation of layer. Also, spread the powder requires another subsystems for the motion. So these are the key components. I think it's since we have learned the selective laser centering, it's pretty much same concept, but different energy source and also different materials, right? And also the working condition will be different because we are dealing with metal here instead of the plastic powder. Also, there are some acronyms like the DMSL, DMLM, SLM, EBM, and look at these for what they stands for. Like direct metal laser centering, direct metal laser melting, selective laser melting, electron beam melting, and so on. So I think we have a direct metal laser melting machine in our lab, and Jake is, Jake, are you here? Is the machine you're working with is the sorry, DMLM machine?
I think it's DMLS.
I think what the machine located in the Brinkman lab is this direct metal laser melting machine here. But this shared pretty much similar concepts. So we just introduced the general concept for these processes. Especially the most widely used one, selective laser melting. To start work, the first thing is to prepare the CAD model and prepare the slice file. Then the powder will be loaded to the machine and repeat this two-step process. Spread the powder, melt the powder based on the patterns of each layer, and repeat these two steps. So there are extra steps for the post-processing. Basically, you want to depowder the part because same as the selective laser centering, the build part is buried in the box of the powder. So you have to remove the excess powder on the part after the build. And another thing is the part actually is bonded onto the build platform. There's an extra step to remove it from the build step. Then you have the part. And again, you want to inspect the dimensions, the precision, building precision of the part, and send it to the final finish machines to have a better, to have a higher precision and remove some of these unsmoothness features on the surfaces. So these are the complete steps for using the selective laser melting machine. And we can look at this video to take a look. So as you can see here, this is the powders they use for the process. And basically, this is the setting up of the machine. And as you can see here, the powder is spread, and then the laser beam is guided to melt the powder for one layer, right? So this will be repeated again and again until the whole part is built. Now you want to take out the build platform together with the part. So again, you really want to design your part carefully to make sure the excess powder could be taken out. So as you can see here, this is an open space, right? Otherwise, the powder could be locked in the interior. See, this is the step to remove the part from the build platform. And now it's the inspection. That's the structure light based scanning process to compare the build part versus the geometry, I mean the CAD model. And then this will be put into the machining, I mean a CNC machine for the final finish. There could be some other process to do a simulation here. So that's pretty much what a part is built through this SLM process. So this process actually is widely used, and another one is the DMLS. And this one is launched by EOS, which is a German company. I mean Germany company. Which one's the country name? German or Germany? Oh, it's a German company. And basically what it does is it has the basically if you look at this illustration figure, so what it does is just like what you see in the video, right? So the laser is guided, laser beam is guided to melt the metal powder and for each layer, and a object it will be fabricated in this way. Of course, there will be a powder spread process before each of the scanning of the layer. So the strength for this process is it will produce the parts with high density. Also, because the laser is utilized here, the spot of the laser beam could be very small. In that sense, a very high resolution of the part could be created. That suggests a high accuracy or high precision of the part has. So there is some other weakness for this process. First thing first is that's a cold process. That means the powder these powders are not heated up, and that could introduce a high thermal stress for the parts, which will reduce the good mechanical property and material property of the part built. The build speed is relatively slow. Also, the ultimate sphere need to be controlled because there is a metal melting, and if there's no control on the ultimate sphere, that will be some oxidation there, which will again decrease the mechanical property of the parts. So these are the, I would say, the shortages for this process. So there are some important points I would like to emphasize here. So first thing first is the powder spreading. So in the to spread the powder, actually there are two paths of the roller, the roller to move. So let me draw a illustration here. So for example, let's say this is the build surface, and here's a roller, and at first it moves in this way, and the roller will rotate in this direction, which is a clockwise direction. And let's see, this is a pile of powder here. So basically by moving in this way, and the roller will press onto this powder pile and make it a smooth surface. But usually one pass of motion is not enough. I mean, cannot achieve the enough smoothness. So what the machine does is, okay, when powder travels to the end of on this side, sorry, it will revolve. It will revert the rotation and go back in this way, such that the surface will be further processed, such that there will be a much smoother surface. So that's the spreading process. And another thing is there could be some collisions during this spread because of the warping of the part. So that happens. For example, if you have one layer built, right? And of course, you have a theoretical geometry or height of the parts, but that may not be true. There could be some warping because the thermal expansion. And this warping could, for example, suppose the layer is something like this, right? But due to the warping, it could something like this, right? I just accelerate the warping. It may not be that significant, but even a small amount of warping, let's see if you spread the powder onto it, there could be some collision with here or here. And that suggests us to think of a flexible blade for this spreading mechanism. So there will be a blade connect to this roller, such that this will make sure the collision will not prevent the motion of this spreading system. Because it has some flexibility, there will be some deformation if there are some collision here. So that makes sure it still can pass through these regions. So that's the powder spreading. Another thing is the recycle. As I mentioned, it's very expensive, the metal powder. So in that sense, you cannot afford a unused powder, as you can see in the video. So it's something like if even you build just the hollow part, that's the box of the powder, and what you build is just something like this, a cup, right? right? So that means the volume is just this little. But if you have to have the whole powder, I mean whole box filled by the powder, metal powder. So if you do not recycle the unused powder, that means even for building this much, this small volume, you want to use the whole box of powder. That's a big waste. So the recycling of the unused powder is a necessary requirement. So another thing is the loss traceabilities that suggests some of the especially the applications in aerospace and biomedicals. So what you build, you want to have a you want to trace it, where it's built and what's the condition it is built, and so on. For these kind of applications requires high reliability and require a traceability of the parts. So these are some other requirements for applications using this process. Any questions? Okay. So let's move on. And so there are some equipments listed here. For example, we have the conceptual laser machine here and also the EOS. So for example, these machines, they are quite large, right? And as you can see here, the dimension of this compared to what we have, the desktop level ones, is pretty large. And also they have quite good the powder handling systems. They integrated these handlings together to make sure the powder could be handled well, since it's a very important step. And they have the build speed increased. Basically, here shows some parameters for the speed. And the power of the machine are increased up to 1 kilowatts or even 2 kilowatts. They also think of some other possible improvements, like the lasers. They have multiple lasers such that they could melt the powder, metal powder, in parallel to increase the the building speed. Also, the process monitoring is improved for such machines, and essentially they measure the temperature of the melting pool in real time, such that they could make adjustment to those parameters and the setups. And the modular design of those machines make the repairment and the replacement of the not working part much easier. But still, there are quite a bit of challenges in this process optimization and monitoring. And in the past few years, both the industry and the research institute invest quite a bit in researching the process. What's the fundamental understanding of the process, and especially the melting pool is I would say a focus, as well as the powder, the modeling of the powder particles, which is another essential aspects in this process simulation and monitoring. So what this process can build? As you can see, these are the some of the parts built using this process, and this fuel nozzle is very well-known ones. This is for Boeing, right? And built by GE. And also we have this. This is, I think, this is a bracket for the for the doors on the airplanes. So compared to its original design, you can see the remove of material, but at the same time it has a same mechanical properties. Basically, the mechanical property is not sacrificed, and at the same time the weight is reduced significantly, and also all these ones, and as you can see, this gun actually can be printed using the solid concepts. I mean, using the laser melting based processes. So for the warping problems, if you check this example, for printing a relative larger area of parts with larger area, you can see there's a warping, and now you should be able to understand why there could be an collision, because here and here they are all tilted, right? And tilted upwards. So when the roller is spreading the powder, there could be some issues. But overall, this is a very important process for industries, and this is being researched quite a bit in the past few years, and now, and I can expect more investment and research will be continuously put in this process in the next few years as well, right? So basically, as you can see, the thermal stress, what I discussed in the previous slides, and that can introduce a distortion to the metal parts. For example, this metal parts has a thickness 30 millimeter, which is 3 centimeter. Oh, that's pretty thick plate, but as it warps around 3 millimeter. So how to tell it is warped? Basically, if you put it onto a flat surface, there is some tilted regions. See, this is the warping happens here, and that is because the thermal stress in the direct metal laser melting based processes, and that could introduce a serious inaccurate of the building part from this process. So another post-processing we mentioned is the build part need to be removed from the build plate because the part are metallurgically bonded with the start plate. So there must be a way to remove it. Basically, it's not possible to use your hand or to just like what people did for other process, use knife or some other tool. For this, that requires a wire EDM, the electron, what's the name again? Okay, that's the wire EDM or the spark machining. So what it does is basically there will be some wire used to cut the part from this platform, such that you will have a separate workpiece with the build platform. So this is the poster processing. So this EDM, actually its full name is electric charge discharge machining. So that is used to remove the part from the build platform. So that, I mean, I just add one more word here. So as you can see here, even the post processing is so complex and costly. That suggests, well, this is not for commercial users. I mean, consumer level users. It's for the industry, and that is for business. So that's why people are thinking of some cheaper and easier ways to print metals, and that is what the Xerox. I mean, in the previous lectures we discussed those inkjet based printing, right? That's much easier than this one, and that could reduce the cost and simplify the process and the post process, which is considered as one alternatives for many applications. Of course, I think for many applications requires the high precision and good mechanical property. You have to use this selective laser melting. But for many other cases, if you just want to have a metal parts with good conductivities, with fairly good precision or part accuracy, you can probably think of other ways, right? Instead of using this a complex, expensive, and troublesome process. As I mentioned, there is another process to handle the metal powder, which is the electron beam melting. So different from the selective laser melting, which utilize the laser as the power source. This EBM utilize the electron beams. As you can see here, this generates the electron beams, and again, this electron beam will be guided onto the build platform to melt the metal powder such that one layer will be created. So this for here, the electron beam replace the laser, but it does a similar job, that is to melt the powder particles. So what's the strength for this process? Well, the density of the metal part is really good. And it's a hot process, different from the selective laser melting, because the powder will be heated up during the process. And in that sense, the thermal stress will, very little thermal stress will be induced during the process. And compared to the laser melting, it has a relative faster build time, build speed. But the weakness is also obvious. Because it utilizes the electron beam, they want to really keep a vacuum chamber. Why? Because otherwise, the ultimate particles will have depletion with the electrons, and that will defocus this electron beam, and such that the build accuracy cannot be kept. So that's why a certain level of vacuum need to be achieved within the chamber. And another thing is the material, less material are available for this process. And that is because the material conductivity is one consideration for this process. So these are the weakness for the ABM process. Let's look at some of the facts for this EBM process. Basically, a thin layer of metal powder is spread over the platform, which is similar to the selective laser melting. And then a 4.8 kilowatts electron beam is scanned selectively over the powder bed and melt one cross-section layers of the, slice of the part. And then the powder is spread again, and the process will be repeated again. The scanning process. So these two steps will be repeated alternately again and again until the whole part is built. So here shows a built part from the electron beam melting, the EBM process. So let's look at a video here. All right, then you have this blade built here. So I want to stop here, and let's come back at 11:05. All right. Okay, let's continue. All right. Okay, I think there's another captionist. Let me. Okay, there we go. So there's another video to show more details for the EVM process. You can see multiple electron beams are shown there. So these are, this video shows the part are built for the this artificial joints and or bones. Okay. So here shows many parts built in using the EVM process. As you can see here, again, complex geometry like these ones or these ones could be achieved using the EVM process. Also, those lattice patterns are utilized for building for design the parts. All right. So here, the powder spreading mechanism here is called RIX. So it is made of steel. Again, it is flexible for preventing the collision. We mentioned this, right? So that is because there could be some warping or deformation of the built part, and to prevent this collision and enable the completion of the powder spreading, the steel part blade are made of flexible materials, right? So the key components for EVM is this electron beam gun. So basically, this here shows the illustration for this part, for this component. Basically, there will be a accelerating voltage of 60 kilovolts. Pull a stream of electrons off the filament. So here is the filament, and this high voltage will be used to pull a stream of electrons from this filament, and an electromagnetic field will be used to determine the spot of the beam. I mean, spot size of the beam, such that you could control the feature size on the built part. And then this electromagnetic will deflect, will steer the beam to the desired location. That is for the guidance of the direction of these electron beams. So as I mentioned, this process has to be in a vacuum environment because if the air particles would scatter the electron beam will make this beam defocused such that the build accuracy cannot be achieved. So that's the electron beam guns. Oh, I think I forgot to mention these two. So for this steering, this is in high speed because basically you are just changing the electromagnetic field instead of actually moving any parts, mechanisms. So that is pretty fast. So it can achieve like 10,000 meters per second for this steering. And if you have some calculation about this and have a really big number, don't hesitate because it is fast. It is a high number for the steering speed. All right. So some parameters for the EBM. First thing is this spot velocity, usually in 10 to 1,000 millimeter per second. And also the spot size. It can be controlled by the electric and electric magnetics. And it ranges from 0.1 to 0.4 millimeter. The power of the beam, 50 to 4,000 watts. Also, this will lead to a melt zone in the powder, on the powder bed. So the layer thickness ranges from 50 to 250 microns. And again, this whole powder bed is heat up to a working temperature, as we mentioned in the previous slides. It is a heated process, not a cold process. So we have the patterns for the melting for the meltings. Basically, the contour of this of one layer could be scanned firstly or lastly. That's up to the choice of the user. And the interior regions is something like this, right? You can see these smaller rectangular regions. Basically, you can raster all the ways from side to side, as long as you think it will fill all the area of inside this contour. And you can also melt smaller squares as shown here. Basically, you are divide the whole region into smaller squared regions, and scan them one by one. Because the steering speed is pretty fast, that will make this whole scanning pretty fast. And you can see in the video, it's the steering is pretty fast. So for the material, it's very expensive again. I mean, same as all those powder-based processes. Its cost for the material is pretty high, such that what they could produce a near net shape. So a near net shape means the geometry of the part is very close to what you designed, and that means there's very little material is wasted. To achieve it, the powder need to be handled pretty well. In that sense, that increased the cost for the metal powder preparation. So another thing is the it's related to the working principle of this process. So the electron from the electron beam must have a path to go, right? After the strike onto the surface of the part. So that suggests the material must to be a conductive material. That's why the polymer and the ceramic are not good material, cannot be utilized in this process. So the metals will be the one which have a good conductivity, such that the electron beam will go through these materials. So the powder bed is need to be very carefully set up, because the charged particle repel one another if they have the same type of charges. So that will be a challenge for this kind of process, and that's why the polymers and the ceramic cannot be utilized here, because if because they don't have a good conductivity here. If they are charged with the same type of particles as I mean, if they have the same charges for their particles, they will repel each other, and that will mess up your chamber and make the process fail. So that's why a polymer, ceramic are not good materials. Only the metals can be used in this process. Sorry. And what's the relationship between the electron beam and the melting pore diameter? So basically, the electron beam has a spot size of approximately 0.1 millimeter, and based on this spot size, the melting pool has a diameter roughly 1.2 millimeter. But that's also depending on other parameters set there. But you can see a roughly order of 10 times in terms of the size of this E-beam of the beam size and the melting pool diameter. So the this powder hopper or the powder spreading design has an advantage, that is both sides of the powder is spreading from both sides, and that saves a good amount of time. And another point here is the vacuum, right? Why the vacuum is necessary for this process. Again, the electron could hit the gas molecules, and that will defocus the electrons in electron beams, which will make the process lose control, and have a poor build accuracy. So the powder bed is preheated to reduce the thermal stress and the thermal distortion in the material, such that such kind of warping and the distortion of the final build part could be reduced. So there is a centering conducted of the powder around the part. Why this is this happens? That is because again, the electricity conductivity, electrical conductivity is the major concern. If the powder is centered, it has better electric conductivity, and that will make this process work better. So the powder, I mean, after build of the part, basically, you want to keep it inside the chamber without being exposed to the cold air. That is, again, if the powder is in high temperature and it gets exposed in the air, that could be the oxidization happens. So that's the major reason you want to keep the door closed before the powder cool down, right? That's the main reason here. So in the machine design, if you want to look at what happens inside the chamber, and there should be a viewport, right? And for the viewport, what's the material you want to put there for the window? Actually, you want to have the leaded glasses because this process, we have the electron there, right? And together with the electron, there will be X-rays generated. That's dangerous. To protect the user, the glasses need to be made of leaded glasses. I mean, the windows need to be made of leaded glasses such that it prevent the X-rays to hurt people. So that's some other points for this processes. So again, this spreading powders design, basically the overall thought beneath is still to prevent the collision because the distortion of the parts. If you paid attention to the video I played, during the post processing, there's a need to blast off the excess powder, right? But it's not using the pure air to do it. Instead, the same kind of metal powder is utilized to blast off the excess, to blast the excess powders to avoid this cross contaminations. That's the reason why the same kind of powder is utilized. Same kind of metal powder is utilized. So there's another details that is a certain amount of helium gas is fed into the chamber over the powder bed. And the main reason here is to neutralize the charges. And that's the main reason we have such a process. So through all these discussions, you can see it's again very complex and tedious work associated with this process, and that again caused the high cost for this process. But again, is the build quality and also the good material and the mechanical property of the parts. But when you think of the applications, you have to justify these efforts and also the cost for the associated with the process. So if we look at some of the melting part, the velocity of the beam varies from this range 10 to 100, 1,000 millimeter per second. And the layers usually 0.1 millimeter thick. So some parameters will determine the energy delivered to this build platform, such as the power of the beam, the spot size, and also the scan speed, right? That's similar to the laser-based. So for different material, there are different absorption characteristics for the electron beams. And thin walls will have thick blocky parts if we want to heat up the powder, preheat the powder. So these are the different setup you want to play with before the actual build of the part. Basically, some of the solid metal will stop electron beams faster than the loose powder. Also, that will conduct the heat in different rate as well. So this suggests the powder will be, the preparation of the powder will be, the preparation of the powder will be essential for different parts to build. And that again will require extra consideration and extra work, right? So if we talk about some calculations as we did for other processes, here we have a equation about the heat input. So if we could see, if we look at this equation, basically this equation describes approximately the melting pool depths. So you can always rearrange it to solve some unknown variables with some known variable substitute in here. Let's look at these variables. So Z here represents the melting depths, and here is the beam power, also the temperature risk during the process. Kappa means the thermal conductivity, right? D is the beam diameter. V, the beam velocity. Rho is the density of the material. And C is the specific heat. So basically, I think it's a specific heat capacity. There must be missing a capacity here. I will correct it. But as you can see here, there are many I mean, there are many material-related variables or parameters, which are usually given if you have the material determined. But the important thing here is still the units. You always need to unify the units such that you will have the correct result. I realize there was problems for your homeworks because of the exchange of the unit that caused little problems. So I would like to remind you again, these units you need to pay attention to, and that will really change the results. I mean, if they are inconsistent with each other. So let's look at an example if we have some given numbers. Sorry. So we have 60 kilowatts voltage, right? And also a beam current of 20 MAs. So some temperature also given. The surface temperature 1,200 Celsius, and the melting temperature, that is this much. Then you could compute the temperature raise, which is required here, right? Temperature raise. See, so you can use these to do this computation. And the thermal conductivity, that is this. The beam width, that is given. That's the beam beam diameter, or in other words, that's the beam diameter, right? These are the same, beam width and beam diameter. And the velocity of the beam given, density also given, and the specific heat capacity given. Then the unknown is what's the approximate depth of the melting pool. So basically it is asking what is Z here. So I mean, this is straightforward, right? Just plug in all these known values. Again, the units, you need to be very careful. So we have a power. I mean, we need to compute the power. Oh, there's only one thing here. That's the voltage and also the current given. You need to calculate the power yourself by multiplying them together, right? Compute the multiplication of the two, and turns out this is this much. Basically, this K and the M cancel out, right? This is 10 powered by 3. Oh, writing is so bad. This is 10 powered by 3, and this is 10 powered by -3. So these two will cancel out. Essentially, they are 1. And then you only have volt and A here. And turns out ampere and V here. And turns out you have the unit watts, right? So also the watts actually is equivalent to a joule per second. And turns out you have 1,200 joule per second. So what is the temperature raise? As I mentioned, basically it were given the two temperature, the surface temperature, which is the initial temperature, and the melting temperature, which is this one. And use this melting temperature minus the surface temperature, you have the raise, right? Thermal conductivity. Again, you want to convert it. So basically, this watts, you can always make it joule per second. But here is centimeter. You want to change it to millimeter, convert it to millimeter, right? So there's a little tricky for the solid for the density. Sorry. So here the density is given for the solid metal powder. It's see here is the word solid, but it is melting powder. It has a little different density. So the assumption is the loose powder will have not much more than 64% of density of the solid metal. So you have to use this number and times 64%. It turns out you have a smaller density for the melting powder. So basically you want to be very careful, see what is given here. There's a possibility the density of the powder is given directly. Then you don't need to do anything. That's what you need. But here it's the solid metal is given. I mean, density of a solid metal is given. Then you need to do this little calculation here. And this here is cubic centimeter. then you want to convert it to a cubic millimeter. Now you could use it. So for this specific heat capacity, here is a joule per kilogram and convert it to gram, and that unifies all the units, right? Here, all the units are unified, and then plug all the numbers in the equation. Turns out you have 0.75 millimeter as the melting depth. So this is how we could utilize this equation to do some calculation. For some other questions, this melting pool depths could be given, and some of the other numbers could also be given because they are associated with the material. But this power could be a unknown, right? Basically, you know everything, but not the power. Then you just use the same equation and do the reverse computation such that you have the power, or the voltage is given. I mean, the current is given, but the voltage is not given. Then you compute the power and use the current to come up with the voltage, because the voltage times current is the power, right? So these variations you have to understand, but the centric thing is to understand this equation such that you can utilize them, utilize this equation. So any questions so far? Nope. Okay, good. Let's move on. So for the melting, there are some. So there are some consideration. That is the vaporization. So especially for those alloying elements, with certain temperature, as well as there are a high vacuum level achieved during the process, there could be some vaporization happens. So you have to keep in mind what is the condition for certain elements to be vaporized, and that's a little tricky question you want to figure out before you could utilize this process. So for example, if you have this alloy, 7075 aluminum, with the aluminum, zinc, and Mg elements here. So basically you want to know which one has the highest melting point. So apparently the aluminum has this one. And then there could be some question you want to figure out before you start the process to determine whether this alloy metal powder could be used using the EBM or not. That is, well, if you melt this powder at 1000 degrees, and there's a vacuum level which is 10 powered by 3 torr. So is there any concern about the 3 elements could have vaporization, right? You understand what is vaporization, right? So basically that is the metal elements will change the state to the air state, which is undesired during the process. So that's why you want to be very clear if this will lead to if this temperature, let me find my, if this temperature together with this pressure will lead to vaporization for any of these elements of the alloy. So if there is, that means the process cannot be used such a condition. You want to change the condition, or there's no way to achieve it. Then this material cannot be used in the EBM process. So that's the rationale for you to figure out these ones. So that's why we want to look at this this chart, these curves. So on the left hand side, basically you have the vapor pressures in torr, and on the top you have the temperatures. So each of the single curve represents a vaporization curve of each of the elements. So let's look at our question. So first of all, I can draw a let me draw a curve, or let me draw a straight line here. So let's see, here is the one I think I really need a pen here. Let me try to use this pen, touch pen. So what you could do is, well, you find this this pressure in torr. Basically draw a horizontal line here. Oh, that's very tricky. Okay, maybe I have something wrong, but roughly, okay. And then find out where the melting point of these. So you have 1,000, right? So that's here. Then draw a vertical line. So basically here is the intersection point. So what you want to look at is the, for example, if you want to look at the aluminum. So where is the aluminum? Basically, this curve, that's the curve. It's very tricky to draw a line here accurately. But you get the idea. So for example, that is, in this case, basically, if you have a temperature to 1,000, what is the intersection of the 1,000 with this curve? So that's something like here, right? That is, well, that is the vapor pressure to be 10 power by -5, which is even lower than this one. So that means there will not be vaporization happens. If we have 100 degrees Celsius with such a pressure. So that's how you utilize this curves. Or you could fix this pressure, right? So let's say you have the vapor pressure to be 10 powered by -3. Then what's the temperature alumina will start to vaporize? So if you look at roughly, it's basically that's the point, right? That's the intersection point. But if you go all the street to here, I would say that's something in between 1,000 to 1,500. I would say like 1,300 or 1,250 something. That means up to that, if the temperature is higher than that, which is 100 and 250, aluminum will start to vaporize. But at 1,000, no, this will not happen. The vaporization will not happen. So that's how you utilize these vapor pressure curve as elements. If some conditions, the temperature and the vacuum pressure is given. Any question for this? So you got it, right? Okay, good. So there's a size change of the part built in the during the process, because there's it has a high temperature during the build, and the part will cool down after the build completed. So there will be shrinkage as the part cools down. So in that case, during the design stage, the size of the STL or the CAD file need to be scaled up, such that the parts after the cool down will be the right part, will be the right size you want, right? And there are some guidelines you could think of. For example, for this steel alloy, what you could put as the scaling factor is 1.4%. And for this titanium alloy, basically you want to specify a scaling factor 1.0083% for X and Y, and differently for Z. So that is because, again, the building accuracy for X, Y, and Z are different, right? That's why there are different scaling factor. I think there should be a percentage sign here. I will correct this and re-upload the before I upload this lecture notes. So for the cooling process, so basically, for example, if we are looking at the cooling of steel, that is again, this cooling is in the vacuum, because you want to prevent the oxidization, right? And so it cannot be very slow for the steel material, because if the cooling is slow, the part will be very soft. I mean, if you want to have a rigid part, I mean hard part, you don't want to have a slow cooling. And basically, this process can also not be very quick. That is if you have a high amount of heat, and also if the part immediately get exposed to oxygen, that will be a high oxidization. Basically, that's kind of the very challenging problems. You cannot either open the chamber door immediately, or let the cooling slowly. For this one, you will have a oxidization, and this one you will have a soft material property. So how could we this be overcome? That's a very interesting question to think of. And to deal with this, there's the time temperature transition curve you want to understand first. And that describes the rate at which the temperature drop affects the crystal structure of the material. You know, for the metal parts, the crystal structure is essential. So to understand the rate of the temperature drop will affect the crystal structure of the metal material. That's essential. As you can see here, along this axis, that's the temperature, and here shows the time. And basically, this is the temperature in Fahrenheit, and this is the temperature in Celsius. So the crystal structure will substantially will be the substantial influence factor for the material property. So that's why we care about the crystal structure that much. And again, very slow cooling lead to a softer and a ductile material. Because of the larger grain are formed if the cooling is slow. On the other hand, the rapid cooling will usually lead to a harder, stronger, and as a price brittle material. So that really depends on the what kind of material property you want to have, and that will determine what kind of cooling strategy you want to use, either a rapid cooling or a slow cooling, right? But for the titanium, that's a little different. Basically, this titanium is easily oxidized, so you must keep it into the build chamber, maintain a high vacuum to maintain a oxygen-free environment. That will prevent the oxidation of the titanium. What happened here? Okay, and more seriously, there could be a fire if you allow the air into the build chamber when the titanium is still in high temperature. That could be a fire. So that's very dangerous. You don't want to open the door before it cools down. It cools down, right? And another thing is for the excess powders, that's very expensive. You know, titanium powder, alloy powder is very expensive, and you have this much this much powder inside the chamber, and you don't want to make them all oxidized. Since this titanium material is very strong, at the same time it is light, so in many medical applications it is used to make those implants or the artificial joints, right? So as we already know, you don't want to have the oxygen to be inside the chamber. So to make sure this will be the case, you want to fill the helium gas to the chamber during the cooling process of a part made of titanium. A good thing is with this helium gas, that speed up the cooling process from 10 to 12 hours down to 2 to 3 hours, which is a significant reduction in terms of cooling times. So again, the post-processing is essential. You want to you want, after you take out the material, I mean the part, the centering material need to be removed, use different ways. For the loose powder, it is vacuum away. But there's also problems for the safeties, right? For steels, it can be vacuumed relatively safely. But for some other material like aluminum, titaniums, and magnesium, or some other powders, which have a high chance to get exposed if, I mean, high chance to get explosion. That's not a good way to vacuum without using the grounded vacuum with the explosion-proof motor, because there could be the electric sparkles, and that could cause the explosion easily. So you have to make sure the vacuum with a explosion-proof motor. So that's pretty much. I think that's pretty much I want to cover today, and we will continue the discussion next Monday to finish up the metal printing part. And the last part will be some motion component design for additive manufacturing. Basically, you have learned quite a bit processes so far, right? And many of them shared very similar components because it has similar building patterns, which is layer by layer and then accumulating in the Z direction, right? Something like this. So what could be some of the common principles or common designs for the printer itself instead of just using it? That will be the last topic we will cover. So if you want to work in direction to like improve the processes, improve the machines, and at least understand how it works such that you could fix the problems or make adjustment easier, that will be essential for you for the last part of this lecture. I mean, this course. So, and that will be introduced next week. Any questions? Nope. Okay, I think that's pretty much all for today's lectures. And again, if you have any questions, just let me know. And otherwise, let's meet next week.
Thank you, Professor.
Yep,
Have a good
no problem. Yep.